Welcome to Numerical Analysis. Today, we are going to explore one of the most reliable and fundamental techniques in mathematics, the bisection method. If you have ever tried to guess a number by asking if it is higher or lower, you already understand the core logic of what we are about to learn. Let us dive in. Now that we are ready to begin, let us think about how you find a word in a physical dictionary. You do not read page by page. You open the book in the middle, see if your word comes before or after, and discard the half you do not need. You repeat this until you find the word. The bisection method uses this exact same foolproof logic to find the root of a mathematical equation. A root is simply the specific value of x that makes the function exactly equal to 0, which visually is where the graph crosses the horizontal x-axis. Before we can just cut things in half, we need to be sure the root is actually there. This brings us to the intermediate value theorem. For this method to work, our function must be continuous, meaning you can draw it without lifting your pen. We also need a starting interval, defined by 2 points, a and b. The absolute most critical requirement is that the function must have opposite signs at these 2 points. If you are above ground at point A and below ground at point B, you absolutely had to cross the surface of the earth at some point. That crossing point is our root. So we know the root is trapped between A and B. How do we find it? We calculate the exact middle of our starting interval. This formula is as simple as taking an average. We add our lower boundary A and our upper boundary B together and divide by 2. This gives us C, our midpoint. Conceptually, this is the mathematical equivalent of opening the dictionary exactly in the middle. If A and B are far apart, our search area is large. By finding C, we are preparing to cut that search area perfectly in half, zooming in on the true root. Once we have our midpoint C, we need to figure out if the true root is in the left half or the right half. We do this using a simple sign test. We multiply the function's value at the start point, f of a, by the function's value at the midpoint, f of c. If the result is less than 0, it means one value is positive and the other is negative. They have opposite signs. This tells us the root is trapped in the left half between A and C, so we can throw away the right half. If the result is greater than 0, the root must be in the right half. Let us look at this visually to make it completely clear. Here you see a continuous curve representing our function. Notice how it starts below the horizontal axis at point A and ends above the axis at point B. Because it goes from negative to positive, it must cross the 0 line at the point labeled root. We calculate the midpoint C, which sits exactly halfway between A and B. By checking the height of the curve at C, we see it is still negative. Since C is negative and B is positive, we can visually confirm that the root lies to the right of C. We just cut our search area in half. Before we move on, let us see this with a concrete example. We want to find the square root of 3, which is exactly the same as finding the positive root of the equation f of x equals x squared minus 3. First, we need a starting interval. We know that 1 squared is 1 and 2 squared is 4. Since 3 sits between 1 and 4, the square root of 3 must be somewhere between 1 and 2. Therefore, we will set our lower boundary A to 1 and our upper boundary B to 2. We have successfully set up our search area. Continuing with our setup, we must verify that the function actually changes sign between these 2 points. We plug our starting point 1 into the function. 1 squared minus 3 gives us negative 2. Next, we plug in our ending point, 2. 2 squared minus 3 gives us positive 1. Because we started at a negative value and ended at a positive value, we have proven that the root is definitely trapped between 1 and 2. Now, we calculate our first midpoint, C1, by adding 1 and 2 and dividing by 2. This gives us exactly 1.5. Now we need to test this midpoint to see which half of the interval contains the root. We plug 1.5 back into our original function. Squaring 1.5 gives 2.25 and subtracting 3 leaves us with negative 0.75. The result is negative. Remember that our upper boundary at 2 gave a positive result? Since the function is negative at 1.5 and positive at 2, the root must be between them. We throw away the left side. Finally, we find our second midpoint by averaging 1.5 and 2, giving us 1.75. We are getting closer to the true square root. Now that we have used this method on a simple square root, let us apply it to something harder, a cubic equation. Consider the function f of x equals x cubed minus x minus 1. We are told to look for a root in the interval between 1 and 2. We apply the exact same logic as before. First, we check the lower boundary. Plugging 1 into the equation yields negative 1. Then, we check the upper boundary. Plugging 2 into the equation yields positive 5. Since the signs are opposite, negative 1 and positive 5, the root is absolutely confirmed to be between 1 and 2. Continuing with our cubic equation, we find the first midpoint by averaging our two boundaries, 1 and 2, which gives us 1.5. We now evaluate the cubic function at this specific midpoint. Plugging in 1.5 gives a positive result of 0.875. Now we compare signs. Our starting point at 1 gave a negative result, and our new midpoint at 1.5 gave a positive result. Because the sign changed between 1 and 1.5, the root must be in this left half. Our new smaller interval is from 1 to 1.5, successfully narrowing our search. So we have seen how to calculate the root step by step. This brings us to why this method is so incredibly important in the real world. Many advanced mathematical methods are faster, but they can fail, crash, or get confused if the equation is too complex. The bisection method, however, is like a slow but unstoppable tank. As long as you start with a positive and a negative point, it will always find the root. Because of this extreme reliability, it is heavily used in computer science, embedded systems, and safety-critical software, where a failure to find an answer is simply not an option. We have covered a lot of ground today, so let us review the key takeaways. The bisection method is a highly reliable, step-by-step search strategy for finding the roots of equations. It relies entirely on the intermediate value theorem, requiring a continuous function and a starting interval with opposite signs. By repeatedly calculating the midpoint and keeping only the half where the function changes sign, it steadily traps the root in a smaller and smaller space. You have now mastered a fundamental tool in numerical analysis. You simply cut the problem in half over and over until you find your answer. Excellent work today.